All right, you've just completed a lab on buoyancy. Now for a little theory. Let's imagine we take an object and hang it from a fishing scale, spring scale. Now, if you take that and then lower it into the water, you'll find the reading on the scale is reduced. The reason for that is when the object is here in the air, the spring scale is supporting its weight. So the force from the scale and the scale reading are just the same as the weight of the object. However, when you bring it over here and lower it into the water, well, the weight of the object is the same. But now, in addition to the spring scale pulling up on the object, we also have the water pushing up on the object. And because the water is now pushing up on it, well, the spring scale exerts less force just to hold the object here at rest. So the spring scale reading is reduced. And it can be significantly reduced by this upwards force from the water, which is called buoyancy. All right, so where does buoyancy come from? Well, let's look at an object, and we lower it down into the water. Now we know that there's water pressure here pushing on the object, and there's air pressure up above. And at first glance, we may think, okay, so the force of pressure from the water is going to push on the sides of the object. Those are supposed to be horizontal, and going to push up on the bottom, and going to push down on the top, and maybe all of those just cancel out. Well, it turns out they don't. And the reason they don't, oh, that's frustrating. I was just trying to make that horizontal. The reason they don't is that pressure increases with depth. You're going to do a lab on that concept a little later. And so the upwards pressure on the bottom here is actually greater than the downwards on the top. And as a result, there's a net upwards force on the object. So the sideways pressure forces cancel out, but the down and up don't. So because pressure increases with depth, the pressure here is greater on the bottom. So the bottom pressure is greater, and so there's more, or I should say not more, but I should say the upwards pressure force is greater than the downwards. i.e., we have a net upwards force that's called the force of buoyancy. So that's where buoyancy comes from. It's the difference in the pressure forces at the top and bottom. All right, now let's go about deriving an expression for this. Now we'll see later in the course that the pressure force varies with depth, and it turns out the pressure at a depth d here is atmospheric pressure. So that's the pressure pushing here on the surface, right? That's the weight of the atmosphere, the air pressure, plus a little bit more due to the weight of the water. And this is the density of the water. This is the Earth's gravitational field, 9.80, and this is the depth d that we sit in the water. So we'll use that to do a little derivation. So that'll be the pressure down here on the bottom. On the top, we just have atmospheric pressure, and we use a special symbol for atmospheric pressure, P naught. So if that's the pressure on the top, then the downwards force on the top, well, a pressure is a force over an area, so a force is going to be a pressure times an area. So that's the amount of downwards pressure force on the top of the object. So the pressure at the bottom has increased, so we've got the pressure due to the atmosphere plus a little extra pressure because we're at depth d in a fluid here. And so the force on the bottom, which is directed upwards, we just said it's going to be greater than the downwards pressure force on the top. It's the pressure times the area. So we sub in the expression for the pressure and multiply by the area. And so the resultant of these two is the buoyant force. So that means we're going to have to take the upwards one and subtract the downwards one. And we see that this P naught A term cancels, and we just end up with this term, rho G d A. So density of the fluid, gravity field, depth, and then cross-sectional area. So when we view from above, the object has an area A and is submerged by a depth d. But of course, that's a base area times a height. That's a volume. And this volume right here, d times A, isn't the whole volume of the object. It's actually the submerged volume of the object. So this net pressure force then, which we said is the buoyancy, we see that it depends on the density of the fluid, the Earth's gravitational field, and the amount of the object that is submerged in the fluid. And we reminded you from elementary math that that submerged volume was the cross-sectional area times the depth d that it was submerged to. Now this result we could show is consistent with the principle of Archimedes. Apparently Archimedes was having a bath and he realized that the water was supporting him. And then he thought, a little thought experiment. He said, if you could freeze that water surface in some way and take me out, so it would look sort of like this, then you could take a pitcher and fill back in that cavity that his body had left. And you would arrive at another stable situation with the water totally filled in and just a level horizontal surface. So what he said is, in some way, he must be equivalent to that much water. So his weight was, or rather, the upwards buoyant force from the water, which was acting on him, is the same as the weight of the displaced water. So the force of the water pushing up on him, that's the buoyant force, that's equal to the displacement. And we could derive our previous result from this idea as well, because if we start with the definition of density as a ratio of mass to volume, cross-multiplying, we can solve for mass. Weight in physics is mg, the mass of the object times the gravitational field. So if we multiply this by g, and then rearrange a little bit, then we see that the weight of the displaced water is exactly rho times g times the volume that was displaced or submerged. And so that's the same as the result that we derived on the other page from the difference in pressure forces. All right, so that completes our derivation. Let's do a sample problem. Let's find the force of buoyancy on a rock sitting at the bottom of a pool. And it's not fresh water because of all the dissolved stuff in there. Ooh, that's a lot of dissolved stuff. The density has gone up quite a bit. Okay, so here we are. There's the pool. And it's a spherical rock sitting on the bottom of the pool. Let's move it so it's on the bottom. Come on, there we go, that looks better. All right, so let's consider the forces. What's pushing or pulling on that rock? Well, obviously the rock's got weight, so there'll be a force of gravity. The Earth pulls it downwards. The bottom of the pool pushes up on it. That's called a normal force. And the water pushes up on it. That's called a buoyant force. And since the rock isn't moving, all those forces have to be balanced. So in physics, the weight of the rock is mg, the mass times the gravity field. The force of a surface pushing up on an object, that's called a normal force. And then this is the force of the water pushing up on the object, and we were calling that a buoyant force. All right, so our analysis, oh my goodness. Our analysis starts with an equation that says forces are balanced. So that means the two upwards ones have to equal the downwards force. So we've got the water pushing up, and we've got the bottom of the pool pushing up. Then we've got the Earth pulling down, and that's the weight. So that is a true statement. We're asked here ultimately to find the force of buoyancy, which is this one, but because we don't know either of these two quantities, this equation isn't useful. So let's also consider the principle of Archimedes, the fluid equation. According to this idea, the force of buoyancy from the water is the density of the water times the gravity field times the volume of the object that is submerged or the amount of fluid displaced. Now let's think about that for a second. So this is the fluid density, which in this case is the pool water. And we're given that value in the problem. This is the Earth's gravity field. That's 9.80 newtons per kilogram, or meters per second squared. And then the displacement in this case, well, the entire rock is submerged. So the entire rock is displacing water. And the rock is a sphere. And the volume of a sphere is 4/3 pi r cubed. And we're given the radius of the rock. So as a result, we can use this principle to calculate the buoyant force on the rock. So we'll substitute in the given values. So that was 1112 for the density, 9.80 newtons for every kilogram is the gravity field, and then we have 4/3 pi. It was a 25 centimeter radius rock. So in terms of the units, notice that the kilograms cancels. This will be meters cubed, which will cancel with this meter cubed. And the only thing that will survive is newtons, and that's good because Newton is the SI unit of force. So let's calculate this. So I'll start with the radius cubed times, where's the pi key? There's pi, times 4/3 times 9.8, kind of working backwards here, times the 1112 density. We get 713 newtons of buoyant force on that rock. Okay, so there is a derivation of this result, the idea that the buoyant force comes from the difference in pressure forces on the top and bottom, and a sample example. At this point, your job is to use this approach to solve another problem that will be submitted as part of your lab report.